My name is Robert Kissel. I'm a solutions architect for AWS. I've been with AWS for about 3.5 years, and during that time frame, I have actually had the pleasure to work with FINRA the entire span of their cloud journey. And my technology focus is big data and machine learning, and how those two have a natural and sometimes unnatural symbiotic relationship. Today I'm here with John Hitchingham, Senior Director for Engineering at FINRA. And we're here to discuss the benefits of the data lake, how FINRA performs trade analytics and market surveillance on AWS. So let's talk a little bit about the pillars of a data lake. So the first pillar is scale. So storing and analyzing all of your data centrally. Ingesting your data quickly without predefined schemas, and being able to separate your storage and your compute, being able to scale both of those components separately. The second pillar is cost. Pay for only what you need and pay for only what you use. And utilizing diverse services and being able to optimize your costs. So being able to understand your utilization and performance, and being able to adjust your services, your features, your applications. Next is security. So we have encryption at every step, whether that is the encryption that you bring to AWS or utilizing one of the AWS services. Having explicit control of all ingress and egress, whether that is through security groups, network ACLs, or access and identity management. And then having compliance and governance at the data access layer using the AWS native services. And then the final is agility. Big data doesn't mean that it has to be all batch processing. This could be data that could be streaming in from IoT devices or from advertisements. Being able to mix and match your on-cloud and premise applications and your resources. So a moment ago, I just mentioned that using something like Amazon S3 as your centralized storage. Being Amazon S3 is scalable, secure, and cost-effective multi-tiered storage service. But getting your data to S3 becomes a little bit of the challenge. So that could be done if you have massive amounts of data. It can be moved via Snowball within days, or Snowmobile if you have massive amounts of data. Through things like streaming with Kinesis, being able to utilize direct connections to move your data. Or using the database migration services to migrate data stores. And then what are you going to do with that data? So your processing and your analytics can come in many forms. It could come from your own custom applications running on-premise or running in Amazon EC2. It could be utilizing one of the managed services like EMR. Could be using, QuickSight or Athena for those business intelligence and or queries. And then being able to utilize DynamoDB to be able to catalog your data, being able to create a meta store so that you can access your data in utilizing fast queries and or Elasticsearch for your enterprise search functions. We have Cognito, we have API Gateway to be able to gain authentication and authorization access to your data. And then being able to protect and secure your data. So utilizing KMS, Amazon KMS for your encryption, utilizing your own encryption modules, and identity and access management. So now I want to turn the mic over to John Hitchingham to go through FINRA's implementation of their data lake and their analytics and surveillance.
Thanks, Robert. Hi, everybody. I'm John Hitchingham from FINRA Engineering. And today I'm going to share with you how FINRA performs trade surveillance and analytics on its multi-petabyte data lake in AWS. So first, what is FINRA? FINRA is the Financial Industry Regulatory Authority, a not-for-profit organization authorized by Congress to protect America's investors. And it does this through oversight of over 3,500 broker-dealer firms and over 600,000 broker-dealer individuals in the industry professionals in the US. It also ensures the integrity of America's markets, monitoring over 99% of the equity and 70% of the options activity in the US, looking for fraud, insider trading, market manipulation, and abuse. How does FINRA do this? Our market regulation division pulls in data from outside entities, broker-dealers, exchanges augmented with third-party reference data. We bring it in, we validate it, we run it through a series of processing transforms to normalize the data to feed automated detection models. Those automated detection models will look for anomalies in the data. When they find them, trade anomalies, event anomalies, kick out an alert to a case management system, where analysts will then go and use a series of interactive analytic tools to go explore around the anomaly to see whether there's an issue there that requires regulatory follow-up or not. In parallel, we have a team of data scientists. They're always working to develop new detection models using a variety of tools, and then those get deployed and built into the process as far as the detection models go. This entire operation truly is big data, up to 75 billion records per day, over 20 petabytes of data, now up to 25 petabytes of data, actually. Supporting major exchange clients. We've had pieces of the system running in production for over 3 years. The entire portfolio supporting our market regulation division has been running for 1.5 years in production in AWS. So how do we run it? Implementation-wise, the architecture we use is what we call internally our managed data lake architecture. And the key to this is we've taken the silos or puddles of storage, query, compute, and catalog that existed in our on-premises environment, and we've remapped those to services in AWS. So instead of clusters of Hadoop on-premises, instead of data warehouse appliances and databases, we have a series of services in AWS. Catalog, for catalog, we use a series of open source catalogs. For storage, we use S3. We also use some Glacier. And for query compute, we use a variety of Amazon analytics, or AWS analytics services and compute services, primarily EMR, but also Lambda and also Redshift. And what this lets us do is by mapping to a series of services, we can now scale out without limits, both in terms of processing capacity and storage capacity, so that when there's disruptions or unplanned activity, it becomes a non-event to deal with it. We've also broken down the data silos in our organization so that all the data is now available and accessible through a centralized catalog and basically a single storage medium where it can all can be accessed. So key to the managed data lake is the data catalog. And when we started our journey to the cloud 5 years ago now, we had a set of unique requirements that we need to have satisfied by our catalog. For one, we wanted to be able to manage storage, manage objects in the catalog at the business level, not just the physical level. That way we could have different underlying storage mechanisms underneath. We could reference data, whether it be stored in a relational database or whether it be stored on S3. We also had business requirement to be able to track data versioning and data lineage as part of our business process workflow. We also wanted the ability to capture metadata, again, not just technical metadata like schema information and location information and partition information, but also descriptive business metadata about the objects that we were cataloging. Also important was the ability to be able to trigger events. When new data arrives and gets registered with the catalog, we wanted to be able to do eventing and triggering off of that, and a variety of other requirements. So as I said, we started looking 5 years ago when we started our journey to the clouded catalogs that were available commercially or open source. We didn't find any that met our requirements, so we developed our own. Internally, we called it data management. Today, it's available open source as the HERD project, H-E-R-D, available on GitHub. And this is the catalog that we use today as the core of our managed data lake in AWS. So as an example, I talked about kind of some of the requirements that we had. One that I mentioned was data versioning, data lineage. Why is this important to us? We get those data sets from those external providers. We do that series of transforms and process on it to have an output data set that we do regulatory analytics on. Occasionally, we'll get corrections. Actually, frequently we can get corrections from those upstream providers where we get a new amended data set. And we need to be able to track both the original version of the data along with the amended data that the provider provides. So we also need to track through down to the outputs that resulted from that data, because there's a case that the data set that we use to run regulatory analytic on might need to be rerun or updated because it might impact the regulatory decision based on the new data that comes in. So by tracking all this information in the catalog, we make it easy to do impact analysis and to go out and determine whether or not we need to rerun any set of analytics in our portfolio. Another example, of the things that we're doing today to build and extend the catalog, records management. We're building a records management capability on top of the storage level of APIs, so we can track through a centralized tool the records that we manage in the cloud instead of having to use a separate out-of-band process with manual activities as part of that. Another example of what we're doing is user interface on top of the catalog so that our analyst community, our data science community can go and browse, search, and explore the data sets that are available out there. As I said, we're capturing business metadata in addition to the technical metadata so they can search for do business-related searches, find the data sets of interest, and then they can go through and grab the technical metadata that they need in order to go out and figure out where to access and query and start using the data. This is something that's available today in our internal version of the software, looking to open source it either later this year, if not first quarter of next year. So again, the data catalog is kind of key to what we do. We do watch the emergence of new catalogs that are out there, such as the Glue catalog. At this point, our business requirements, the only thing that's out there that meets them is the HERD catalog, so we continue to build and invest upon it. So with the catalog and S3 as a storage layer, that becomes the hub of our entire processing pipeline. So data comes in from external providers. It either lands directly on S3 or it can come in through other feeds like an SFTP feed we have for legacy interfaces. Data comes in, it gets registered in the catalog after landing on S3. And then we can do a series of processings against it. We can do validation, we can do ETL, we can run those detection models. And in each of those cases, the process starts by kicking off a workflow process that reads from the catalog, finds the metadata that's necessary, and then pulls data off of S3, or in some cases we can query, in many cases actually, we can query directly against S3 and do the processing. So we can go up and go through that validation process I talked about, that ETL transform process, the model detection process. In each case, the inputs read from the catalog in S3 and write back to there as a result. We can even run interactive analytics against the data. For a lot of our use case, we can keep the data on S3 and using open source query technologies like Presto, like Spark, we can query directly against the data on S3 without having to do ETL out of there. In some limited cases, we do ETL for performant query for certain types of query, but for a majority of our use cases, we can directly query against the data on S3, which is one of the big advantages of the data lake architecture. The other thing about this is by isolating these different functional planes, we're able to both scale out if there's a performance, there's increased load that might impact our ETL processing. There's no impact on our automated detection routines, our detection models, or our validation. Additionally, it makes it really easy to swap in different tool sets as the different technologies evolve in the different areas, and we can still integrate them in to one whole. So kind of going through these areas in a little bit more detail, I'm just going to briefly mention our ETL processing. So we have something we call the ETL framework, which is a tool that lets our developers write ETL. We primarily do it in SQL as the language right now for our ETL. And then they can go ahead and deploy that as part of a pipeline that can get triggered based on a schedule, or it can get triggered based on events coming out of our data catalog. So new data arrives, gets registered, can trigger off one or more ETL events associated with that. It's also able to read and interact with the metadata in the catalog to go find out on S3 and instantiate the DDL necessary to go out and do the processing against all that data. I think people that watch Amazon know there's a new product that's available called Glue. We're currently evaluating it. It's still missing some features that we're looking for, but it's along the same lines of the processing that we do, the capabilities that would exist in a service like that. So physically, from an implementation perspective, how does the ETL work? We have a separate EMR cluster, Elastic MapReduce cluster, for each process that we run. So when we need to trigger an ETL, we go and we spin up an EMR cluster. As part of the bootstrapping process or the startup process of that cluster, it will go out, it'll read, interrogate our catalog, find the information it needs to do its processing, go out, read that data from S3. Again, in many cases, we can just query directly against S3. It'll go through its workflow, and then we'll terminate the cluster at the end of that workflow. So a big advantage of that is that we can get extreme parallel processing across our work sets, with a complete isolation between the different workloads. So if there's increased demand in one particular area of ETL processing, it doesn't impact any of our other ETL processing. We're able to do that too, live all these clusters spinning up and terminating on a regular basis. We're able to do that because of spot pricing. We can pay pennies on the dollar, saving anywhere between 70 to 90% on the dollar through the use of our spot pricing. Pretty much the majority of our workloads that we run, our batch workloads, all run on spot. We've also had increased savings from the recent introduction of per second billing, because a lot of our workloads also will spin up and they'll run for less than an hour. So we're getting additional savings now from that too. As I mentioned, a lot of our ETL, or the majority of our ETL, is written in written in SQL. We've been using Hive as the language when we originally started going to the cloud many years ago. We're now moving to using Spark for better performance and some of the language features that the Spark platform supports as part of that as we go forward on the portfolio. So it really is truly dynamic processing. By having all these different workloads as separate EMR clusters, we can spin up to tens of thousands of EC2 nodes a day on EMR at peak, and then we can go back down to just a few hundred when the need goes away based on processing. That lets us respond to events like market fluctuations and the market data we need to process, where fluctuations can increase, volumes can increase 300% day over day. It also lets us respond to unanticipated business demand. So we can react quickly to it. So again, it's a truly dynamic environment, servers coming up, servers going down on a regular basis, adjusting just to the demand and capacity that we need at any given point in time. So moving on from ETL processing to interactive analytics. And this is actually something that's very powerful on the data lake. Given all the data that's out there on S3, using the right architecture, it's possible to go do interactive query against all that data. So the way that we do that typically is we run Presto, which is an open source SQL query engine. We run it on top of EMR. And technologies like Presto and also like Spark have the ability to define data files on S3 as something called external tables for all the database people out there. And that lets you directly query against the data while keeping it out on S3. You don't have to do an ETL process to load it up into an area where you can go and query against it. We're able to do that by populating something called a Hive Metastore, which is a catalog, an open source catalog for defining all the data objects that tools like Presto and Spark can use. And we do that by populating events from our herd data catalog. So as new data sets get registered, we replicate the information over to a Metastore catalog that can easily integrate in with Presto and Spark out of the box. So given this now, our analysts, our data scientists, they can use thick clients, any sort of JDBC or ODBC client, and they can go ahead and now do exploratory ad hoc queries against the data that's out on S3. They can do it securely. We're able to integrate in with our corporate LDAP for authentication. We're able to use the Hive Metastore for authorization control, again, integrated in from information from our Active Directory. And we're able to encrypt all the channels going backwards and forwards from the data out on S3 using SSE and KMS, server-side encryption and key management system encryption, all the way through out to the client. And so again, this really becomes powerful because, in our case, one of our production stores, we have 4 petabytes of data out there in the cloud. It's all available now, and analysts can start querying it within seconds and get results back in seconds. And that holds true for 4 petabytes. That would also hold true for 10 petabytes, 100 petabytes. As the data lake grows, your ability to go in and access any portion of it and start querying on it instantly without having to do any ETL process still remains. So that's really a powerful thing from the data lake architecture for interactive analytics. And there's a lot of different things in this table here just to kind of go through. One is capturing over on the right-hand column. We store all our data sets in sort of a canonical text format where we keep the data in a format we can use any sort of tool to come and query against because pretty much everything speaks text. But we also make a copy in a performant query format, ORC or ORC format for use by our query tools like Presto and like Spark. And as you can see, if you move to a format like ORC or ORC, you can get extremely fast performance for a lot of queries. We're able to run queries against billions of rows of data, 2 billion rows of data on S3, and get answers back in seconds. Also, we've been working with Presto for about 2 years now, and the performance has improved a lot over those 2 years. It's good. In our case, we have a lot of queries that are just filtering type queries, but even a lot of the queries that we had before around joins, and also some windowing functions where we had to move it to another technology like a Redshift to get performant query processing, we can now directly just use Presto running against S3 for our use cases and get performant query. And again, because all the data is on S3, it's not just a question of having to have one application that gets used to go out and query this. If we want to, we can go spin up additional clusters all running against the same data set on S3, whether that's for workload isolation, whether that's for additional capacity. And so we have the ability, if user demand exceeds expectations on our primary cluster, we can just go spin up another, and we have more capacity for our users to use. In fact, what we're doing today is we're now not just using this for exploratory ad hoc queries for users, but we're actually building applications on top of this approach. So we have applications that are using Presto and EMR, running SQL against that as a back end, keeping the data out on S3. In fact, it's a whole set of applications that we've built to do this. Everything from applications to let users self-provision data marts to do exploration on data sets, to visualize depth of market at a given point in time. And also we've even integrated in with our case management system. So in the majority of these cases, we're in a situation where we don't have separate analytic databases for these. The data sets sit out on S3. We leverage Presto on the front as a query technology that we can go ahead and query on the back end. I said we leverage Presto for most of them. That's not true in all the cases. We still use Redshift as part of our Diver application, which lets people provision and explore data marts for some certain query performance scenarios. We also use HBase technology for something called our fast order lifecycle application, which lets users go ahead and view the trade lifecycle of any given trade or set of trades in the market. So this is really big data. It's 700 terabytes of data in the application. We keep it all, though, on S3 because we run it on EMR. EMR has the ability to run HBase and keep the data sets on S3, which lets us continue to use the data lake architecture for that, for significant cost savings and operational benefits over the way we did it before, which was to run all that data locally on a cluster. So again, a lot of operational cost and management benefits from running the data lake approach, and it's not just one application, it's not just ad hoc query, it's a whole suite of business applications that we're building on top of this design. And it's not just user applications, data science. As I mentioned before, we have a whole team of data scientists that work on developing new models and new automated detection routines and a variety of other work, data science work going on at FINRA. And again, the data lake lends itself to that too. The data sets are out there, they're all available on S3, they're integrated in and searchable searchable through our catalog. So the data science community can go out and use their catalog to go find the data sets. Once they've found the data sets, they can, on their own, through self-service, provision an environment where they can go and start doing processing now and get working very quickly against those data sets without having to wait for technology staff to go find the data, retrieve the data, provision an environment for them to go to do their work, which really accelerates the pace of data science that we've been doing. We have a couple different platforms that we use on the data lake for data science. Just at a basic level, that ad hoc query capability on Presto can be used for data profiling and some degree of data engineering. We also, at the bottom down towards there's a application called the UDSP, Universal Data Science Platform. And what that is that's an EC2 box pre-configured with a set of data science tools so that our data science community through a web application can go out and provision an environment with all their software stack on them. It can be everything from a small machine, all the way up to a really big R-class machine. It'd be very easy to make it an X1 class machine, where they can go out and they can do single machine processing for their data sets. And this is really good for data sets that go up into the tens of millions in the few millions of rows of data. We also use Spark running on the Databricks platform with interactive notebooks to do processing using machine learning libraries to process bigger data sets. So this is when you're up into the range of billions of rows of data, and we do that processing. But all these tools can be brought to bear, and it's very easy to bring new tools to bear, again, all working against the same data sets and the same catalog on the back end. So I mentioned how the data scientists, they develop the detection models, spend a little bit of time talking about the detection models and kind of how we deploy and use them. An example is our cross-market surveillance model. That's something fairly unique that we do because we're in a position to bring in data from the different exchanges and also through our own order reporting system, a trade order reporting system called OAT. So we bring in data from those sources, from trade reporting facilities, from the ISG audit trail, and we run it through a normalization process so that we can now trace trade activity across all these different market centers and the firms that are out there. And this becomes the basis that we use to drive our automated surveillance models or detection models. Additionally, given that data set, as I mentioned before, there's interactive exploration of the data using tools like that diver tool for people to self-serve explore the data sets, and also that depth of market tool. Those can leverage the same data sets on the back end in S3 to go do their analysis. Implementation-wise, the processing of our detection models is very much like our ETL. Every detection model runs as its own EMR cluster. It gets created, it does its processing, and then it terminates. Loading data from S3 and registering it back in the catalog and writing it to S3 when it's done. Or it can also go through and, again, process directly against S3 in a lot of cases, having to avoid that expensive data load process. Parallelization is still there. Because we have this degree of parallelization, we can run our workloads, as many, whatever workloads we have, we can just keep scaling out with no clusters to go and handle the processing. That comes in handy a lot because we'll run into situations where I talked about where we get those upstream data corrections and we need to do reprocessing. Now, in addition to running, the previous day's processing, if we need to reprocess something from several weeks ago, we can go ahead and we can do the processing against that in parallel with no impact on the SLAs of the current processing. So in a case before, finding the capacity to be able to do that and respond to the business request to do the reprocessing could take several weeks to a month. Now we can do it in less than a day. From a technology standpoint, similar to the ETL processing, when we started out, we were using SQL on Hive as the technology for doing the processing. Now we're moving over to using Spark. We're porting over our detection routines from Hive to Spark because just running basically the same SQL on the same EMR size clusters, we can see anywhere from a 60 to 90% speed up in runtime, which is since we only run the cluster as long as we need to, that directly impacts the bottom line and improves our cost posture by switching to the faster technology. But for our detection models, it's not just a question of moving to Spark just for increased performance. When we started, back before we went to the cloud, we had rules-based detection models. We were running them against a variety of data sets in data warehouse appliances, in Hadoop clusters, on premises. And a big challenge we had there was just getting the data to the right environment where we could actually do the processing, finding it, moving it, getting to the point where we could do processing, dealing with our capacity challenges. That was a real struggle that we had before we went to the cloud. As part of the journey to the cloud, we addressed those challenges with our centralized catalog, with the use of the data lake. We no longer were moving data. We didn't have issues with finding data, and we could bring the capacity that we needed to bear against the data whenever we needed it. But from a technology standpoint, we're still doing this process where the detection models were written in SQL based off of requirements that were developed by data scientists who may have been using other tools and technologies to come up with a model. And then we had essentially mapped that to sort of a rules-based, program implementation that would run in SQL in the cloud. What we're doing now is we're moving from a rules-based detection regime to a machine learning approach to our detection models, where we're able, instead of building models by data scientists that could have to get recoded in a different technology and to a set of requirements by developers and engineers, we're able to integrate that into one process. So the benefits being, we've smoothed that development pipeline for machine learning, for detection model development, and then we have, then we've also gone through and we have streamlined that process, and we've also made it possible so that we can detect and find events with those models we might not have found with a rules-based approach. And the framework that we do it on is something we call our dynamic surveillance platform. What that is we leverage, as I mentioned before, Spark and the machine learning libraries in Spark. And now we run that currently in Spark on top of the Databricks environment, but we've integrated it in with our data catalog, our herd data catalog. And using that in the data on S3 makes it very easy for data scientists to, again, get working, start developing, finding their data sets that they need and are of interest, bringing them in, profiling them, doing their feature engineering, and then doing their model development and testing, on a platform. But we also augment those data scientist people with engineers who can also help at the same time make sure we're building the models out for resiliency and performance. And by doing that, we can now, with the same technology stack, promote that model as a notebook to our production environment, and then schedule it and run it, as a batch mode there, a headless mode there, as a response to events for our surveillance. So we've eliminated this kind of hard handoff between the data science community and their language and their tool set and the production model tool set, so that it's possible to get a seamless pipeline to go across the stacks. So I've talked about the data lake and the different components of it, ETL, automated model detection models, interactive analytics. I want to spend a little bit of time talking about the kind of the foundation that underpins our data lake. And we call it a cloud management platform or cloud management framework. And it's the set of environments, processes, and tools that lets us build and operate secure and compliant applications on the cloud. And I want to talk about two things that are really important to us as a regulator, security and compliance. For security, Amazon has a shared security model where they're responsible for the underlying infrastructure and the security of the services. We, FINRA, as the customer, are responsible for configuring it to meet our security requirements. And as part of our journey to the cloud, we made a pretty significant effort, investment in time to understand how to configure these tools properly to meet our objectives. And so, we're able to achieve isolation of the different environments in a variety of different ways through VPCs to isolate the networks, security groups, to do host level isolation. We're able to isolate within our accounts the capabilities of the individual services through the use of IAM roles associated with each application. We have encryption of all the data at rest and in transit. We heavily leverage Amazon's key management system, or KMS, that we found integrates very well with a lot of the Amazon services, so that it's very easy to achieve a breadth of encryption that's much greater and easier to implement than we could ever do before on-prem. For authentication, we're able to integrate in IAM with our internal corporate Active Directory, so we don't have to manage individual keys for the different users that go in. We're able to manage all our users still using our native Active Directory tools in our corporate Active Directory, and we can federate the logon then to access AWS services, not just the console, but the different services that our development community needs to go and access. So it makes it a lot easier from a management perspective. And then from a monitoring perspective, for our security analysts to do their SIEM reporting, we record all the infrastructure events, change events, we record it, and we have Splunk that we use to go ahead to build dashboards and alerts off of that can drive, bring an analyst, a security analyst to come in and go take a look if there's an event that requires exploration. And there's security, and then there's compliance. So we have a team of system architects and security staff that define the policies. In our data center before, in the on-premise world, those policies would typically be paper documents that administrators would then have to go follow to make sure that we were actually doing what we said we should be doing. In the cloud, it's provided us an opportunity to transform that to enforce this all through automation and programmatic approaches. So we've developed a series of tools that lets our development community basically ensure if they're going to go out and build an application stack, that application stack is going to get built to our requirements, our compliance requirements. We also have tools that make sure for security groups, they're properly leveraging the security groups that are defined and approved by our security team in the building and design of their application. And same thing there's a similar tool for IAM groups too, or IAM roles. And then a variety of other applications that we've built too. This whole suite of tools is available to our developer community, who can then use this on a self-service basis to go out and very quickly get up and running and building applications in a compliant way in the cloud. We give those development teams full access to an approved menu of services in our development environment. From there, they can go and build their application, but if they promote up to higher level environments, test or QC or production, those all have to be done via automation. So, there's no code or applications that go to production unless it gets there through an automated process, an automated deployment pipeline. And there's a couple different advantages from that. One is obviously through automation, everything's going to be consistent as it's going out and getting configured and deployed. The other, from a compliance perspective, that's attractive is that we can really reduce the number of people that have access to that production environment. Whereas before, in our own data center, we might have dozens of people, system administrators, database administrators that would need to have access to that environment. Now, because we use automation, we're able to limit that to a small team of release management staff and operations staff. Occasionally, we do have need, sometimes there's things that you can't go ahead and invest in. I should add, the other key to making that work is we take all the log data and event data and we put that off into locations where we can go access it from Splunk. So we'll put it off to S3 or we'll put it off to another source. We can then go investigate and explore it through Splunk. And We've also built in a lot of self-healing capabilities to our applications. So in a lot of cases, if there's a fault in production, the easiest solution is to just kill the instance and restart it, rather than go ahead and try to troubleshoot like an active live instance that's out there. In some cases, we do need to put people in to production to go get on a host, to go look at something. Again, we build a series of tools that lets them do that on a temporary basis with a full audit log. So we have a much greater degree of traceability to the exact events and actions that are going in production. As I said, we kind of emit these events to a series of logs that are out there that are searchable and explorable through Splunk. Between a series of Splunk reports and compliance reports that we've developed ourselves, we're able to do a couple different things. We're able to build scorecards to show back to our compliance staff, the security staff, the enterprise architects, and how the applications are doing. And that's also information that we can share with our auditors when they come in to audit our application portfolio. And we've been in the cloud now for 3 years, as I said, in a production environment with multiple applications there for a year and a half. So we've experienced a lot of audits in the cloud. Going to the cloud, it requires, sometimes we found a bit of a conversation change with the auditors. An example is in the on-premise audits that existed before, there was a particular control that we had to maintain a server inventory for each application that was reviewed and approved by the project manager for that particular application. Well, we go in and we have the audit in the cloud, and we don't have anything like that because the servers are dynamically being created and destroyed on tens of thousands a day, right? So what does that really mean? That required a conversation with the auditors to say, well, what's the real risk here? We understand the control, what's the risk? So we go back to the risk, which is obviously that if you don't have a process to track your server assets where your data is, you might actually inadvertently lose that data, or risk of losing that data through not properly managing that process. So the conversation with the auditors is that, well, in our architecture, the data is on S3. We have a series of controls and mechanisms in place to protect and control access to data there. We need to rewrite the control to reflect how the risk would manifest itself in the cloud. And we're able to have that conversation now because we've been through several rounds of that with our auditors. So again, just another example of experience that we've been able to build by working up in the cloud for several years in a production capacity. So kind of going back to the data lake overall and benefits of it that we've seen. The data lake architecture has really let us go ahead and get a handle on our data through data management. We can now find and explore data and find out where it is. We can explore it. We can make it accessible all throughout its data lifecycle. Because of the scaling capacities, the scaling ability of the cloud, we're now able to respond to things like market fluctuations or unexpected business demand. It's a non-event now, which used to require a lot of people to go out and respond, in kind of an emergency mode. The systems are all now designed to just automatically scale and deal with that. For reporting and investigation, we can now respond much quicker to regulatory reports, reporting requests, because we have a much greater amount of data that we can keep online as part of our architecture. And the analysts can go ahead and ask bigger questions of the data because of the increased capacity of the architecture. So before, where they could only deal with potentially 100,000 rows of data to do their exploration and interaction, they can now deal with tens of millions of rows of data, or even 100 million rows of data. For the data science community, the existence of that catalog and the ability to self-provision environments has accelerated data science in the organization, making it much easier to do. And as I said, we've gone through and we've collapsed all these different silos of information into a single view of the data that makes it easy to go out and access and find. Done this all at a run rate that's, total cost of ownership is 30% less than our on-premise environment before, while meeting the security and regulatory requirements that we have as a regulator. Security and compliance requirements that we have. I don't know if we also have here at FINRA as part of AWS, this is one of 5 presentations in total, so there's 4 others that will be going on at reInvent this week. Just as an example of an indication of the experience that FINRA as an organization has built up across a wide variety of people with building and operating production workloads at scale in the cloud. So, for my portion, I would just leave it at the fact that if you're in the financial services area or that you're in the regulatory area, and you're starting off on your journey to the cloud, or you're in the process of your journey to the cloud, and you're looking to accelerate and make it go faster, we've built up a wealth of experience that we're happy to share with others in the industry, others within the community, to see if we can help provide a way to learn from us and see if there's ways that you can accelerate your journey to the cloud. And with that, I will turn it back over to Robert.
So we have a couple of mics set up. So if anyone has any questions, please feel free to head to one of the mics.
Can you actually go to one of the mics? So there, yeah, because we're recording it in the back. Thanks.
I'll ask a question. One of your pillars I noticed wasn't data resiliency. Resiliency from what we might call an availability or disaster recovery point of view. Now, I'll focus the question a little bit more. I mean, given the benefit a little bit of time, S3 can provide us availability and data resiliency. I guess my question would be in the ingress portions where you're getting those feeds from the different sources where you're getting feeds from, did you meet any particular challenge in sort of safe storing and creating availability and resiliency of data at the ingress point?
At the ingress point, you mean before it goes to S3, or?
What we might call, typically bringing data into a system, you safe store it. Things like synchronous storage between different data centers.
Right.
Right. So in that ingress point, trying to get it so you can safe store your data that's coming in from your data sources.
Yeah. So again, in a lot of our use cases, we're able to write data directly to S3. And so by writing it to S3, from the client, you persist it to S3 as the service, and then S3, and that's, again, one of the huge advantages, under the covers, it's handling that automatic replication across multiple data centers within a region. So you're getting that high availability, that high resiliency, redundancy, as soon as you're writing the bytes to the service, basically, that's there. For some of our legacy feeds, we still bring them in through other technologies like SFTP, and there we just have to run a farm of servers, basically. But again, it's the same thing. It's essentially a stream of data coming in temporarily out on that infrastructure with local disk, very quickly rushing to persist it back to S3, where we get that multi-data center resiliency built into it, and we don't have to go through all that engineering work. We're able to just basically the client writes it, and the rest of it's taken care of after that.
On a regional basis, but what about a cross-regional basis?
So it's not cross-region, it's within a region, but there's multiple data centers within a region, and there's isolation between those data centers that we've gone through, and for our requirements, the availability that we can get through that, the resiliency, is far greater than we could get even with different data centers that we were self-managing, whether they be geographically close or geographically distributed.
This side over here?
Yeah, for your success, sort of describing what you've achieved in terms of, before and after, have you developed any metrics around surveillance incidents and looking at things like both scope of market, like do you feel like you're getting a higher percentage of incidents that should be looked at? And then the other one is from a cost save perspective, do you measure cost per incident, and has that gone down as well?
Yeah, I personally haven't gone through to do the metrics on, cost per incident. Again, at the portfolio level across the whole market regulation area, the cost to operate the plant as a whole is, like I said, roughly 30% lower than our on-prem. I mean, I think, we could go ahead and potentially do that work at some point if we wanted to kind of break it down on a per incident basis. But that's not work that I've done personally. From a breadth and richness perspective, as I said, I think the thing that we've been really focusing on is kind of improving time to market and improving, resiliency, the ability to quickly respond quickly to those reprocessing events and things like that from the infrastructure side. What we're really engaged in right now is that kind of evolving the capabilities of the detection portfolio itself through things like machine learning. And that's a process that's really in full focus right now. with additional ramp-up plan for next year.
Right, so you think that overall is going to achieve a greater confidence that you're detecting all of the events you should be detecting and identifying them as significant events?
Yeah, I mean, I think the idea with the machine learning portfolio, besides the efficiencies that I talked about, is that it also makes it, you're going to have events that you may not be able to detect with sort of a rules-based regime, that you can basically get greater, more events are going to come to your attention than you could get that you might not, a priori be looking for just, based on thinking up requirements, so.
Right, okay, thanks.
Yep.
All right, this side over here.
So the data sets that you maintain there, what is your compliance that you need to keep them ongoing? I mean, you're growing to 25 petabytes. Is that the 3-year maintenance of it, or how do you manage cleanup of legacy data set?
Yeah, that's a good question. So we have a data retention policy. A lot of our data is, we keep it for 7 years and then we would destroy it at that point. For going to the cloud, we haven't been in the cloud long enough that we have lots of data sets that meet that mark. So that's why we're now putting in the process like the records management piece and things like that, so that when we get to those events, we need to start destroying records. We've got an automated process in that can do that. So yeah, but the idea is we need to comply with our records policy. So when we reach those thresholds, the data would have to be destroyed. Yeah.
All right, this side over
Was
here.
there one? I think you were waiting longer.
Okay. Do you have much PII or other sensitive data in your data sets? And do you have to tackle problems around one-way hashing and otherwise redacting that data before it reaches the clients?
Yeah, we do. So of the data that we have in the cloud, the vast majority of it would be, we have different tiers of classification. We call it confidential, but requires encryption of the data. We have some small amount of PII data in the cloud that requires, at a minimum, the encryption layer. That's where we're required to use KMS encryption. We can leverage it for ease of use in other areas too. But for the actual data, the pulling it back and rendering it to a user in an application, the client, we also do redacting at the application level of the data sets as they come back. So that's something that's responsible right now. The client application, following a set of processes and reviews, is responsible for building that into the application.
Got it. So that's all handled in EMR, is it?
The redacting of the information? No, EMR in our case generally would become sort of, as in the case of the interactive example, it would be a query layer. So it's kind of like the database backend. We would tend to redact that information typically in the, once it gets retrieved before it gets rendered to the user through the client interface.
Okay, thank you.
What are the different formats of data sets that you have on your S3, especially for using Presto and creating data files in S3?
Different formats in terms of like physical storage format, or?
Yeah.
The majority of our, like I said, we keep a text file format copy of all of our data that we have in the cloud. And then in the cases where we're doing a performant query format, typically we do that through ORC, org file format for columnar compressed. Those are pretty much the two formats that we use. We probably use a little Parquet, as part of our Spark work, but that's not something that we formally, do at the enterprise level. That's just for, users creating their own output tables, and they just chose to use Parquet for temporary tables and things like that.
Okay. Then how do you find access control of a data within a data set?
Access control within the data center or the data set?
Data within a data set. How do you find access control?
How do we define access control? So we basically, again, two different scenarios. One for batch applications, they'll use the catalog to determine whether or not they can have access to the data. And then for interactive applications, that's typically controlled at the application layer to define whether or not the user should be able to have access and do anything with the data.
All right, thanks.
Yep.
This side.
Yes, my question was related to your 3-year journey into the cloud from on-premises environments. You didn't replace everything wholesale all at once. Your end state is a very elegant solution, and all of it seems to live in AWS. But as you incremented into AWS, did you find products that just did not function with a latency difference between maybe its data was there and the application was there, now the data's out
Right.
in AWS, but the application's still here. Did you tackle any problems like that during your migration?
Yeah, as part of our market regulation portfolio migration, we didn't really experience like interactive kind of scenarios like that because the big data sets themselves tended to be in batches or micro batches. So we built a whole mechanism, we call it the data bridge, to basically keep the data sets in sync between our on-premises Hadoop clusters, data warehouse appliances, and the data sets in the cloud. And that replication, we had no issues with that. But throughout the duration, though, we did have cases where we had client applications that were running and needing to talk to, databases, be it Redshift or be it, SQL clusters up in the cloud. And, so we have a direct connection with provision capacity. And, we didn't really see anything significant in terms of a latency perspective, and we could dial up the performance to be what we needed, so.
How long did you have to operate with replication coming back to your on-prem environment for the entire data set?
We basically, so one of the data catalog and that data bridge were some of the first things we set up as part of the migration. So we ran that through the whole life cycle of the migration, really, until there weren't any dependencies on-prem infrastructure for that.
Thank you.
Yeah.
Thank you. Last question.
Hi.
Yep.
I'm curious about your use of KMS. Are you using the bring your own key, or are you using an Amazon managed master key? And also, I'm also curious about your data classification that you mentioned. Is there certain types of data that you've determined you can never put into Amazon?
No, so to briefly, because I know I was told we had to stop in 5 minutes, with 5 minutes left to go, but just briefly on the last one, no, I mean, we have personal confidential information up there in the cloud encrypted through KMS. Basically, we generate the key, and then only the infrastructure is the piece that's managed by AWS as part of our approach, so, yeah. And I think we have to wrap the questions, right? Yeah.
Yep. So we'll be out here actually in the main hall, all the way down at the end for anyone else who has any questions. Want to thank everyone for coming. When you have a moment, please fill out the survey for the session. Thank you.
Thanks.